Starting 6-1 with area. Getting into the subtleties here. Alright. Okay, now I'm going to break this into two parts. One involves integrating with respect to x, the other involves integrating with respect to y. The underlying theory is exactly the same, but you just have to orient yourself in terms of the way the graphs look and notation. Okay, but the underlying theory is the same. Whether it's dx or dy. Okay, part A. Okay. I call this dx scan. Doing a dx scan in the xy plane. Okay. Of course, if you have like the t and w axes, then work with those, but dt and dw. But if you have x and y, we have dx and dy. Now, if you're going to compute an area, then I suggest that you either do a dx scan or a dy scan. All right. Well, what's the example of the dx scan? Here's our classic example. All right. X-axis, y-axis. All right. Here's a graph of y equals f of x. All right. Here's x equals a, x equals b. All right. I want to know the area of this region. All right. Well, come on. What's going to give me the area of that region? The definite integral from a to b. Yeah. So the area here is going to be given by the definite integral from a to b f of x dx. Okay. Now, under what conditions? If. Okay. Now we know that this comes in as a positive contribution. Okay. If f of x is non-negative, or it's at least non-negative. All right. If f of x is non-negative, and also it's continuous. F is continuous on the interval. Closed interval from a to b, we assume a is less than b. Okay, so we assume that area statement is true, provided that we're guaranteed non-negativity and f is continuous. I'm not going to mess with you regarding continuity. All right. Okay. Now here's the thing. Let's say that we want to know the area of a region between two graphs. All right. So x-axis, y-axis. All right. So here's the graph of y equals f of x. Here's the graph of y equals g of x. Here's A. Here's B. So it looks like a Frito-Lay chip. Okay. All right. Now you might be going, well, isn't it kind of arbitrary to have these walls here? Well, we'll talk about that later. We'll talk about where they naturally intersect, these two graphs. Right now we're putting walls in at x equals a and x equals b. In fact, I'll write them down. Here's x equals a, x equals b, right? Just like over here. X equals a, x equals b. Okay, those are common boundaries for our region. Okay, so I want to know the area here. All right, I want to know the area here. Okay. Well, what do I mean by a dx scan? Well, in the sense that, all right, if we go like this, all right, in a way, you can think of it as integrating these signed lengths of line segments. Okay? And the thing is, we can do the same thing over here. It actually does work. Imagine a Xerox scanner. That's like a DX scan. The scanner's going like this. Right? Okay. So how can we express this area? Area equals integral from a to b. All right. Now, it is true that we're going to think of this as, well, what do you think the integrand is going to be? It's going to be f of x. Okay. Well, what is the length, or height, I should say? What is the height of one of these line segments? At x, if we take a fixed value for x, how does it go? We take the x coordinate on the, the y coordinate on the top, minus the y coordinate on the bottom. So it's going to be, given this x, f of x minus g of x dx. And I have several comments to make here. All right, several comments. First of all, when can we say this? All right, well, we can say this if f and g are continuous, okay, and also f of x is basically beating g of x. It's like he's leading g of x. f of x is greater than or equal to g of x on the interval, closed interval a to b, also continuity on that interval. All right, so when does this formula apply if we have a situation like this? All right, if f and g are continuous, all right, and if f of x is always beating, maybe tying sometimes, g of x on the interval, right? Why? Because in order for that formula to work, okay, the f of x guy has to be on top, the g of x guy has to be on bottom. Now bear in mind, it's quite possible that you might have an example where g of x turns out to be the guy on top, f of x turns out to be the guy on bottom, and then you switch those, all right? Which means that the thing to really remember is this here, okay? Remember that the integrand goes top minus bottom. That's the thing to remember, top minus bottom, all right? It's the y-coordinate on top in terms of x, is minus the y-coordinate of this bottom point in terms of x. And it's in terms of x because we're doing a dx scan. If you're doing a dx scan, then these expressions have to be written in terms of constants and or x. All right. Another comment. Actually, it does not matter what sign f and g are, okay, for these various values in here. Okay, in fact, both these guys could be below the x-axis, or there could be a split, okay? It doesn't matter. What matters is that in this formula, f of x is always beating g of x. So the top guy is on top. It doesn't matter if both these guys are above the x-axis, below, if it's a split, they cross over. It does not matter, okay? Now here it mattered, because here we're comparing f to 0. Over there we're comparing f to g, right? F always has to be beating g, maybe tying g, okay? And then we go top minus bottom. Here, this is the special case where g of x is what? This is a special case of that where g of x is what? 0. 0. So here we're comparing f of x to 0, which means that to ensure that f of x is always beating or tying 0, we just have to make sure that this graph is not going below the x-axis on this interval. Okay, so here we're comparing f to 0. Here we're comparing f to g. We do not have non-negativity constraints. Okay, so we don't need f of x and g of x to be non-negative. We don't need that anymore. We just have to make sure that f of x is always beating g of x, meaning time. Okay. I have two more comments. There are a bunch of comments I can make here. All right. What's one rationale for this? Okay. Well, if I take the area under the f graph, this is like the big region, all right? And I subtract off the area under the G graph. The G graph. Okay. Do you agree that if I take the overall region, right? So everything under this graph, including this stuff, all right, minus this gap here, the stuff we want to delete, we get the Frito-Lay chip we want, right? So this minus this gives us the answer. Okay. Now why does that make sense? What's this? It's the integral from a to b of f of x dx. And what's this? Integral from a to b of g of x dx. Alright? And remember, we have linearity even for definite integrals. The difference of integrals is the integral of the difference. Okay. That's one reason this equals makes sense. Yeah.
Does it work out mathematically to like either combine the two functions before you do it, or to do the definite integrals of both functions and then subtract the final answer? Do you get the same answer?
Well, either way, you can do things term by term. Now, if you can simplify by canceling out terms, great, right? But either way...
But what if you actually found the definite integral of f of x and then found the definite integral of g of x and then subtracted?
In principle, that would work. As you might imagine, this is often more efficient because you can often get cancellations.
Okay, I was just wondering.
Yeah. So yeah, generally speaking, you would do it this way. Yeah, that's true. Yeah. I mean, in principle, you do it that way. But here, again, here you tend to be able to get cancellations, but be careful. Make sure that you're subtracting all the terms in here. But yeah, that is generally easier to do, unless you have a bad habit of not distributing your negative number or putting grouping symbols. Anything else? And then finally, my last comment here. All right. This is related to the whole Riemann sum thing. All right. So this comes from Riemann sums. Here's the Riemann approach. Okay. The idea is very similar to what we were talking about before when we were defining a definite integral, except here, what's the situation? All right, so, okay, here's a picture here. Here's A, here's B. Now, here's the idea. Just like in the picture here, we're often going to take a representative value for x somewhere in here. Okay? Just some arbitrary value just to get our focus going. Okay? And as I said before, it's sufficient to look at the height. In fact, well, I'll say sine height, but it will always be non-negative. If you know that the f guy is always beating the g guy, we know this will always be non-negative. Okay? So we take this height here, okay, and that corresponds to like this guy over here. All right? And then informally, we can say that we're integrating these lengths of line segments. That's very informal, though. Okay? Informal. I guess I could erase this now. Okay, so informally, it's like we're integrating these lengths of line segments with respect to x. Okay, and that was true when we just integrated f of x dx also. All right. Now, how does this connect together with that Riemann analysis we were doing from last chapter? Okay. Well, the idea is that in principle you can break this thing up into rectangles, right? You do the partition, regular or no, but you can do a partition, right? And by the way, some instructors do this actually. Sokowski kind of does it. It takes a representative rectangle. And the idea is that the width of this rectangle, all right, technically it's delta x, but guess what? That's going to eventually give us dx when we write the definite integral. Remember, the delta x from the Riemann sum sort of evolves into a dx in the limit when we write down the definite integral. All right, but that's like the width of this rectangle, all right? And what gives us the height? Well, it's the y-coordinate on the top minus the y-coordinate on the bottom. Now you might be asking, are we doing an LRA, MRA, RRA? You know what? It doesn't really matter. And in the limit, it doesn't really matter. We're assuming continuity. Okay, so that's the idea. I mean, if you believe that principle we did last chapter, the idea of breaking up a region into rectangles, right? And then we imagine the partition here getting finer and finer. So the norm approaches zero, right? We've got the norms of the partitions approach zero. Then we're going to approach then the Riemann approximations will approach the exact answer. All right. But it's the same underlying theory. Any questions about that? From now on, I'm not going to draw a rectangle. Some people do that, and Sokowski does that quite often. But you know, in general, we draw a rectangle where we have width delta x. For convenience, I find that that's going to be problematic. So I tend not to draw the rectangle. Some people probably think I should, but I'll dispense with that. Okay, just remember that dx or delta x corresponds to the width of the rectangle there. All right, in the limit, the width shrinks towards zero. Okay, so all those comments, okay, leading up to that, all right? Questions? You're integrating the lengths of line segments with respect to x. It goes top minus bottom, all right? Again, don't think f of x minus g of x, because you don't know. Maybe g of x is on top, okay? You should really think top minus bottom. Based on my picture, it's that. Okay. Questions? Questions? Let's do an example. All right. And this is going to stem from something that we talked about back in pre-calculus. All right. Example. Find the area. Okay. Find the area. This is the last time I'll write this. Find the area of the region. Okay. For convenience on the board, I'll dispense with that. But find the area of the region. All right. Bounded by. Okay. Again, I'll dispense with this later. The graphs of. I go without saying. The graphs of. Okay. Y minus x squared equals 0. And y minus x cubed equals 0. Just being kind of cute here. All right. All right. Now, these steps I'm going to show you, you can do them in various orders. Although here, there is a sort of natural order here. All right. First of all, general, in the xy plane, I can give you equations in x and y, and they could be a bit jumbled up. Well, what are you tempted to do in both these equations? Yeah, solve for y. Solve for y, yeah. So both equations for y. Alright. And by the way, in dx scanning, where the scanner is going this way, okay, like so, hash marks are going like that, then yeah, you solve for y. Alright. Solve both equations for y. So of course, from here we get y equals x squared, and from here we get y equals x cubed. Very natural. It's very easy to do this. If you find that it's very hard to solve for y, it could be a hard problem, or maybe you were supposed to do a dy scan. We talked about that. Alright, so we have y as functions of x in both cases. Alright, second, well, sketch the region. The graphs of those equations, therefore the region. Okay, sketch the region R. We often let R represent the region, so maybe I should have put R instead of A in some of my previous examples. All right, sketch the region R. Now, some people might want to do this first, even. Maybe not so much here. I mean, this helps a lot, right? Okay, but there are some cases where it might actually help you to try to remember what the graphs of these things look like before you try to solve for one variable or the other. So, now, this is where your pre-calc comes in. And I stressed this point in my own pre-calc class. We're talking about the area between the area of the region bounded by these two graphs. Now, you might be wondering, wait a minute, what region are you talking about? There's a bounded region? Yeah, there is. See, a lot of you don't know it. I hope my pre-calc people do. There is a bounded region, all right? Let's talk about this. X-axis, y-axis. All right. What's the graph of y equals x squared? Parabola opening up, vertex at the origin. That's pretty straightforward. Okay, so here's the graph of y equals x squared. Notice what I'm doing here. Y equals x squared. All right, y equals x squared. All right. What is the graph of y equals x cubed? Rising snake. Now let's be careful about this. Rising snake. Okay, I know that he comes from, he's in quadrant 3, right? He starts off negative here, right? Well, he doesn't start anywhere, but, okay, he's coming in, negative, 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 reaches the origin. So we see here, what kind of point is that? That's a what between these two graphs? That's an intersection point. That's really important. Okay? And don't you agree, hey, if x goes out to a billion, and so forth, you agree x cubed is dominant, right? So we know that x cubed is flying out here. Okay, so then the question becomes, well, what's going on in here, right? Now at this point you might be going, I need to do some calculations. So folks, you don't have to go in linear order. You can kind of jump around, right? The equations, the graph, and some more detailed computations. Some of you might be stuck. Wait, I don't know how these graphs compare. Okay, well, let's do some calculations. In fact, let's talk about step 3. You might want, sometimes you have to do this before step 2. Okay, there's no set order. Sometimes you got to jump around. These intersection points are important. These intersection points are important. Find intersection points between the graphs. Okay? Remember before how I showed you these pictures? X equals A, X equals B, these brick walls. Okay? Here, I didn't give them to you, right? I didn't give you an A and B R. Okay? And in fact, here we're not going to get walls, we're going to get points. We're going to get these intersection points that are going to cut off the region. All right, both ends. Okay, it's like a towel, like you're kind of squeezing up both ends. Let's find the intersection points. All right, folks, pre-calculus. To find the intersection points, you solve the what consisting of these equations. It's that S word. System. You solve them simultaneously, right? At what order pairs x, y, okay, will both these be true? In other words, what are the points that lie on both these graphs? All right, find the intersection points. That means you solve the system. Okay, consisting of these two equations. Y equals x squared, y equals x cubed. Here, the substitution is very straightforward. Y equals x cubed. Well, again, basically, you know, at a particular point, y equals blah, y equals blah, blah. You set these equal to each other, all right? Okay, so we have x cubed equals x squared. Okay, by substitution, or just because we know that y does not have a double identity at a point. Okay. X cubed equals x squared. Do I want to divide both sides by x squared? That's dangerous because you might lose 0. Okay? In fact, here you would. Okay, let's subtract x squared. X cubed minus x squared equals 0. Then factor on the left. We get x squared, and what's this other factor? X minus 1. That's very important. Okay? So what are the values of x that would work here? Well, we have x equals 0. That makes sense, right? Because we know we intersect over here. Okay? Or x could be what? X could be 1. Okay? And that's helpful. That means that if x is 1, okay, we know that we're going to intersect. Okay. And we know, by the way, the graph is going to shoot up. Right? The graph is going to shoot up. Okay. Questions? Questions? Well, actually, I asked for the intersection points. And very often I ask you to sketch the region. And very often I'll want to see where these points are. You have to give me both coordinates for all intersection points. So even though for the integral only cares about these values, we should also find, for graphing purposes, the y coordinates. Well, what are we going to use? We can use either one, right? Because remember, at intersection points, both of these have to hold true. Obviously, this would probably be easier, right? Let's use y equals x squared. All right. Well, if x is 0, y is what? 0. It's 0. If x is 1, y is 1. We get lucky. We have a pair of twins here. We get lucky. So what are the intersection points for the graph? For the graphs? 0, 0, and 1, 1. I may as well, I'll circle them. I guess my final answer is an area, right? Okay, circle 0, 0, and 1, 1. Those are my intersection points. Questions? Questions? You will very often have to find intersection points on these problems. And right here, these determine what A and B are. You're not always told them. Okay? This graph is going to end up at a couple of points, not these brick walls. Now notice I left some questions. Any questions? Yeah.
Where exactly is the region?
Yeah, we'll get to that. Notice I did leave a blank space here between 0 and 1. In my pre-calc class, I call this the twilight zone. Because in the twilight zone, the unexpected happens, unless you've seen 100 episodes. No, then you know what's going to happen. Okay. He was dead all the time, dude. All right. All right. It's a doll. Okay. All right. Now, then you might be scratching your head going, so what is going on between 0 and 1? Well, let's do this. Let's test values. Remember we did testing values before? Come on, give me a number between 0 and 1. Half. 0.5. Right? So, if x is 1/2 or 0.5, okay? Well, let's compare, all right? We have x squared, and we have x cubed. Now, if x is 1/2, what's the square of 1/2? 1/25 or 1/4, right? Okay. What's the cube of 1/2? What's the cube of 1/2? 1/8. Between 0 and 1, which is larger, x squared or x cubed? X squared is larger, okay? Now, x squared is larger here, okay? So we know that x squared is larger than x cubed over here, but because of continuity, and because we know that these are the only two intersection points, it's like the test value method, right? If we know that x squared is beating x cubed here, guess what? It's beating x cubed all throughout the window, right, between the intersection points. You all buy that. That's by continuity and by the fact that we only have these two intersection points. You buy that. Okay, so again, here the unexpected happens. If x is strictly between 0 and 1, actually, x squared is beating x cubed, believe it or not. Okay, hence, to answer Rafi's question, where's the region? It's kind of small, but it's there. See, before, you may not have been aware of this fact, but yeah, there is a region of bounded area that's determined by these graphs. There is a region of bounded area determined by these graphs, and we're going to do a dx scan. Actually, either would work. Although I'm sure you people would prefer these equations as opposed to, say, x equals root y, x equals cube root of y. You agree these are nicer, right? So I'm sure we'd rather do it the dx way. We're going to scan it this way. Although either way, dx or dy, we integrate from 0 to 1, either way. Alright. So, that's common here. X squared is always beating x cubed, or tying, on this interval from 0 to 1. Okay, that's important. Why? Because it's important to know who's on top and who's on bottom. Okay? And in fact, you don't even have to worry who's f of x, who's g of x. Don't worry about that here. Just know, well, come on, x squared is going to be on top. Alright? And x cubed is going to be on bottom. Actually, I drew this wrong. I should put y equals x squared there. Okay, I should put my label up there. Sorry. Y equals x squared on top there. Again, it's counterintuitive, right? Y equals x squared is on top. Y equals x cubed is on bottom. Even I temporarily forgot x squared is on top. Okay. Y equals x squared is on top, y equals x cubed is on bottom. At least on the interval of interest. Remember, folks, we only care about the interval of interest. So as far as we're concerned, x squared is beating x cubed. Or time at the end of this. Alright, questions? And see what I said? This region is, it's like when you squeeze the ends of a towel, right? We're cut off here at this point, cut off here at that point, and that determines A and B for us, right? Alright. Questions? Notice that we have not done any calculus yet in this problem. It's been all pre-calc, right? It's been all pre-calc, like the work problem, it's been all pre-calc. Any questions? In this problem, the calculus is easy. Okay, again, you don't have to think number of linear steps, but let's set up the integrals. Okay. Set up the integral or integrals. If you're unlucky, you might need more than one integral. Alright, set up the integral or integrals. Here, this is a very straightforward integral. We're going to integrate from what to what? 0 to 1. Remember, it's a dx scan. Okay, we're scanning this way. That Xerox scanner is going this way. Okay? Remember, it goes top minus bottom. Technically, if you want to be a real stickler, it's the y-coordinate on top as a function of x, minus the y-coordinate on the bottom as a function of x. Lately, I've been dispensing with these because they seem rather confusing to people, but, okay. But, top minus bottom. Bottom line. If you want to know the bottom line, it's top minus bottom. Alright. Given some arbitrary x in here, okay, pick some arbitrary x between 0 and 1, preferably not 0 or 1 themselves, okay? Okay, and we look at this line segment, right, the height of some Riemann rectangle in there. What is the height of that rectangle? It goes top minus bottom. What is that? For that fixed x, what is it? It's x squared minus x cubed, right? For this fixed x, okay, the y-coordinate on top is given by x squared minus the y-coordinate on the bottom is given by x cubed. If you really highlight the points, that might help. X squared minus x cubed. It's the top y-coordinate in terms of x minus the bottom y-coordinate in terms of x. That's what it looks like. On the exam, if I tell you that you just have to set up the integral, you're done here. Okay? On the chapter 6 test, there may be some problems where I just have you set up the integral, and I trust that you could do it if you had enough time to evaluate it. There are other problems where I have you go all the way. Let's say I have you go all the way. Okay, let's evaluate this thing. It's appropriate because we want to review chapter 5, right? Number 5, if you have to, evaluate. But again, on the chapter 6 test, right, on the chapter 6 test, read the problem. If I just tell you set it up, you do not have to evaluate. Okay? If I tell you to evaluate, go all the way. All right. FTC. What's the FTC? It's the fundamental theorem of calculus. Fundamental theorem of calculus. All right. So what's this thing? Equals. I'll put brackets here. I have to find what's that AD word? Antiderivative. Okay. Antiderivative. X squared goes to what? Careful. Not the derivative. X cubed over 3. Again, folks, we know when to differentiate and when to integrate. x cubed over 3 minus, okay, how about x cubed? Goes to x to the 4th over 4, from 0 to 1. And wouldn't it be fun if we had u subs also in there, or trig? They can happen. All right. What do I do? Plug in the 1, the upper limit, all right? So put big old parenthesis, okay, bracket, 1 cubed over 3. Am I doing overkill with that? Am I doing overkill with, okay, I don't need this one. Okay, 1 cubed over 3 minus 1 to the 4th over 4, bracket, minus, well, hey, if I plug in 0, this is 0. Still, I want to indicate this just to remind you, hey, plug in 0. By the way, seriously, sometimes I've given like a point more extra credit if you write down minus 0. If you end up making an error down the way, because at least it tells me, yeah, you know the FTC at least. I'm more likely to give it to you if I see the 0 there. Okay, so you plug in 1 minus, plug in 0. Here we're lucky we get 0. It's not always 0. Okay. What's 1/3 minus 1/4? That's 4/12 minus 3/12. It is 1/12. Okay. Now that's the value of the integral, but bear in mind, it is a geometry type problem. Now, sometimes I neglect this in the notes, I apologize. I really should put the unit. So let's say for example, that I tell you that x and y are in meters, okay? Let's assume that x and y are measured in meters, okay? And what should this area be measured in? Yeah, square meters. I'm very happy that this number is not what? Not negative. Okay, I'm happy it's not negative. If this is negative, if you get a negative result, what did you probably do? You probably misidentified who was on the top, who was on the bottom. In which case, you need to indicate that to me somehow. Don't just say, oh, I'll put the sign. Either redo it, scratch out and redo it. In fact, you know what? Officially, that's what I'm going to say. Scratch it out, redo it. I don't like saying erasing because sometimes people erase the right thing, but scratch it out, redo it. Okay. Question. By the way, if you only have 1 minute left on the test, write down. Okay, switch, boom, boom, switch with these double arrows. Yeah.
All right, so what's the difference between doing this way to get the area than using the Raymond's?
The Riemann? Oh, the Riemann thing, that was just for approximations. Like these chunky rectangles, that'll give you an approximation.
All right, and then the trap method and the parabola method.
Those are all approximations.
But this is exact.
Oh yeah, I'm leaning on the FTC. When I find an antiderivative, try to remember that's FTC. But I don't know if they're with calculus.
All right, so now why were we doing the other ones in the?
Oh, okay, yeah. The reason why I did it for root x minus 1 for that guy was because I wanted to compare the results. But in general, you want to do it if the integrand is something that you can't find an antiderivative for easily. You don't know how to integrate it. What if I give you sine to the 11th x? Really, professionally, you're going to find out how to do that in Calc 2, right? Unless you're integrating from like -1 to 1, in which case the answer is what? Integrand, it'll be 0. Unless there's a special property. Or there's geometry. Root 9 minus x squared, there's geometry. Like an half circle or something.
Yeah.
But if you're not able to find an antiderivative, even with the use of, if you can't find good geometry, right? If there's no special trick like the even odd, well, odd trick for example, right? Then, well, the last resort, approximate. We wouldn't expect to get the exact answer, but we hope we're good enough.
All right.
But it's important. What's the difference between getting, in principle, an exact answer, or at least exact up to a certain number of decimal places, and doing an approximation?
All right.
Well, you might be off here. Okay, questions? So I know it sounds a bit hypocritical because I forget sometimes in the notes, but remember your units, okay? If the original distances are measured in meters, the unit for area is square meters. What's it going to be for volume? Cubic meters. Yeah. So make sure you have the appropriate unit. Okay, it's an area problem. In chapter 5, you don't see it as much because if you're just given a definite integral with no context, then there's no unit to be had. Okay. By the way, the square meters, the idea is that the integrand contributes meters, and the dx guy contributes that other meters thing. So it's like delta x, right? meters squared gets nothing meters squared. Questions? Questions?
If it was volume, wouldn't it be 3D?
Yeah, now that's, what are we gonna do later? In fact, we're gonna do this on Wednesday, actually. We're gonna take, for example, a plane region like this, we're gonna revolve it about an axis. For example, imagine taking this, revolve it around the y-axis. What's the volume of the resulting solid? We're gonna see that kind of thing Wednesday. Now she's sorry she asked. It was inevitable. Don't blame her. It was inevitable. We will get the 3 dimensions.
It's my fault.
Although at least we'll have symmetry, rotational symmetry. You may not have that in Calc 3. Calc 3 is like find the bottom of that TV set. Questions? By the way, this is amazingly beautiful. But that's not so shocking, right? I mean, come on. Polynomial, nice numbers. Okay. We got a nice rational result. That's not so shocking. All right. Now, well, we still have much to do here. All right. We gotta stop gabbing. All right. Let's do another example. Okay, yeah, this is a follow-up, actually. This is a follow-up. What happens if we go further? So let's say that I want to know the region if I put a brick wall out here somewhere. Okay, let's say at x equals 2, yes? Okay. All right. So here's the idea. I have these 2 graphs. Okay, I put a brick wall at 0, fine. I capture that origin again. And I put a brick wall at 2. I want to know all of the captured pieces, the total area of all the captured pieces in between. Okay, so for example, okay, same as before, but x is now restricted to be in the interval from 0 to 2, which means that we have another bounded region. Okay. All right. Now, this is not to scale, but x-axis, y-axis, okay, not to scale, but, okay, so we have this parabola over here, all right, and we have the snake guy. I'll do it in yellow again. All right, we have this, I don't care what happens in quantum 3, but, or 2, but, we have the snake guy over here. Oop. All right, not to scale. Here's 1, here's 2. Okay, this guy we already found, right? Okay, we already found that guy. That guy was 112. Square meters, I know. But we already found this guy from before. Now we also have to deal with this guy over here. Okay? And I want to know the total area of those pieces when I impose walls at x equals 0 and x equals 2. So don't worry about the jump over here. Don't worry about that. All right. So how does this setup look different? Okay, well the first part is the same as before. It's the integral from 0 to 1, okay? Y equals x squared is on top, so it goes x squared minus x cubed dx. We know that was, what, 112. But wait a minute, there's another piece. Plus, okay, now what's this integral over here? The integral from what to what?
1 to 2.
1 to 2, how does this one go?
X cubed minus
X cubed minus x squared, all dx. Remember, you need moving symbols here, more than one term. Okay, why is that? Because we're switching places, right? Y equals x cubed used to be on the bottom here. He's now on top. Okay, whereas here, x squared is now on the bottom. Okay. It's like the 2 parties, right? They go back and forth, right? Okay, so notice, so this is one reason why I don't like to talk so much about f of x and g of x. I do write the template just so that I'm consistent with books, for example. But remember, you're thinking top minus bottom. And come on, if who's on top and who's on bottom switches, then your integral has to indicate that. So you have to split the integral up here at 1. Of course, if you have continuous graphs, where are the only places where they have a chance to switch places, top, bottom? At what kinds of points? Intersection points, if they're continuous, and they will be continuous here. I'm not going to mess with you on continuity on these kinds of problems. Okay? That's the least of your worries. You can assume that. Okay. And by the way, I trust you can do this. All right. This works out to, it's huge relative to that. It's 17/12. So this was not to scale. Actually, this region 2 here is 17 times as big as region 1. So that was not to scale. Right. The sum is 18/12 or 3 halves. Again, square meters. Okay. Question. Yeah.
So are these their signed areas?
No. That's the thing. If you do a definite interval, then you have the whole signed area thing, and it matters if the regions are below the x-axis. But here's the deal. if I ask you, what are the areas, or the sum of the areas, of the regions that are bounded when you impose these graphs here? Does it really matter if we're above or below the x-axis? No. What matters is how these graphs compare to each other. To each other. That's what really matters.
So even though they switch with,
They do switch places relative to each other, but it doesn't. We don't care about what's going on relative to the x-axis. Because remember, for these kinds of problems, we're comparing these two functions against each other, not against zero. Okay. In fact, the way you set these up, look, area itself is never negative, right? Similarly, one check here. Here's a check, in fact. These integrands can never be negative. This integrand can never be negative on this interval. This integrand can never be negative on this interval. Okay, that is one check, by the way. In fact, the check is equivalent to the test value that we just talked about. Test. But no, these guys could be like 1 million miles down, right? They could be 1 million feet down, right? It doesn't matter. We're just comparing them to each other. It is true that sometimes we compare with zero, right? If the x-axis is on top, then it's 0 minus this guy, and that's the way it should be, because it's 0 minus the negative thing. Right. Also, don't forget something that could help you. Who could be your friend sometime? That S word. Symmetry, right? So if f is even, for example, or odd, for that matter. If f is even or odd, okay, then you can use symmetry. Now, if that is even, for example, all right, and you want to know this region here, here's the graph of f, here's A, here's B, here's 0. Okay, clearly you can see how symmetry can help you, right? Then you can take twice the integral from 0 to B, and of course, if you apply the FTC, you'd rather plug in 0 than this negative number here. That's typically the case. Although, even if f is odd, that's also helpful in both cases, right? Over here, if f is odd, the graph is symmetric about the what? The origin. In which case, it might look like this. But then, here's the deal. All right. Well, what would you do? You would take the integral from 0 to b, and once again, what would you do to find the total area of the region bounded between the graph of f and the x-axis? What would you do? Once again, you would or double it. Yeah, you double it. You double what you have here. And you know what? Even if f is odd. So here's a big difference between chapter 6 and chapter 5. Once again, here, you double also, because you want the area. So you take the positive value here, and you double it. What if I asked you, what's the definite integral from A to B of this odd guy? These are opposites. What would your answer be? 0, because these cancel. If I'm asking about the area, the total area of the regions bounded by the graph of f and the x-axis, and these guys, then it's a positive number. It's going to be twice that. Areas are never negative. Okay, if I'm asking for a pure area, areas themselves are never negative, and you never have negative contributions in these geometry problems. Unless you do something really funky.
So,
Yeah.
the interval is, would be 0?
The value of the definite integral from A to B would be 0. However, the total area of the regions bounded by these various graphs will be twice whatever this guy is. Right? It'll be twice this, right? If that's 10 square meters, we have 20 square meters total. Okay? Remember, areas are never negative. Areas themselves are never negative. There's no signing here in that sense. Okay? So in other words, like I said, if you're below the x-axis, that does not contribute a negative number. However, on this side here, the 0's on top. If you use an integral to work this out, then you need 2, because here 0's on top, here 0's on bottom. You see? Basically, you have to flip the sign on this side. If you were to work it out using an integral on both sides. All right. We have more to talk about. All right. Questions? 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 How about dy scans? The underlying theory is exactly the same. This time the Riemann rectangles go this way, right? Okay. But calculus in principle and theory doesn't care, right? However, visually we care because it affects the way we graph things. Hey, I have a section. For the first time, you might want to refer to 1.8 in my pre-calc notes. 1.8. How do you graph x as a function of y? Okay, even my pre-calc people kind of short-shrifted that, but you might want to look at 1.8. How do you graph x as a function of y? Use the principles. sort of similar to that. All right, issue B. How do you integrate with respect to y? How do you do a dy scan? Or whatever the dependent variable is. Okay, integrating with respect to y. Maybe we should have said dependent. Sometimes y is the independent variable. We treat y as the independent variable. Okay. Okay, so what if y is our independent variable? All right. Okay, so what's our classic setup? I just want to set this up. All right. So over here, what if we have x as a function of y? X as a function of y. X equals f of y. Hey, look at that guy. Hey, he doesn't pass the vertical line test. That's okay. I'm claiming that he represents x as a function of y. He does not have to pass the PLT. He has to pass the what? The HLT, horizontal line test. Okay? Given one x, there's no more than one y. All right? This time, here's A, here's B, and here's the region I want. You could call them R this time. R. Okay. By the way, some books use C and D. Okay, some books use C and D. Personally, I actually prefer A and B myself, but you can use C and D. That's what books do. All right. We do double intervals, basically. All right. And then come on. What's the area of the region? The area A of the region is given by, well, integral A to B. This time it's f of y dy. Okay, and the natural scanning direction is going like this, bottom to top. Scanner goes like that, scans the region.
Wait, so,
Yeah. Oh.
isn't it R equals?
I'm saying it's the area of the region R. The region is a geometric object. It's a shape. Area is a quantity.
Okay.
Okay. The region is the actual physical geometric object there. Right. And don't worry, that distinction won't harm you. But since I've been talking about R, okay, R is that region. I want to know its area. Area of the region R, that's A. Okay, that's not the problem. Now, what if we have a gap? Or, we just have two guys. Right, we have two guys, and they create a gap. Or maybe one guy's here, one guy's here. Okay, so let's say we have x equals f of y, and we have x equals g of y. But still, I'm kind of spoiling you. I'm giving you the limits of integration. Okay, here's y equals a or c. Here's y equals b or d. Okay, I want to know the region of that. That looked like the alien, didn't it? Right. No alien. R. All right. All right. And I want to know the area of this region. Okay. Now, what are a couple of reasons why we might want to do a dy scan? Okay. Well, why a dy scan? Okay. Why a dy scan? Well, I can give you a couple of reasons. For one thing, maybe it's easier to solve for x in terms of y, right? Maybe it's easier to write things as x equals, something in y. A function of y. Okay, you can very readily solve for x in terms of y as opposed to vice versa. And also, the region suggests that. Okay, the region scan is easier this way. Okay. Because here's the deal. When I do this kind of scanning, it's going to be a matter of right minus left, correct? Right minus left. Okay. Now, what if I try to pull this stuff? Do you see how a dx scan might be worse? Dx. And then this part's okay. And then, wow, I'm getting a breakup over here. You agree? A dx scan would be awkward. You agree, right? A dx scan would be awkward. Okay. And that means you would have to solve this for y. We're not sure if you can do that. What if you have x as a fifth degree, x equals a 50 degree polynomial in y? That would be a mess.
Question?
Yeah.
What's an example of a function that does that? Looks
sorry?
like that? What's an example of a function that looks like that?
Oh, well, you mean kind of curly like that?
Um,
Oh, well, maybe a third degree polynomial. X equals a third degree polynomial in y. Yeah. Couple of bumps. I'm like Stewie. Couple of bumps.
So it's graphing x as a function of y is the same graph
you know what, all right. The graph of y equals f of x is equivalent to the graph of x equals f inverse of y if you have a one-to-one function. So you're right that so in other words, there are times when we consider the inverting. For example, there are times where we turn a cube root function into a cubing function. That happens sometimes. So we do sometimes do an inversion. That is true. That happens sometimes. Right? That's this idea of solving for one variable in terms of the other. But you don't have to think of it. You don't have to worry about the theory of inverse functions, though. But you're right. That is part of the process. This idea of solving for one variable in terms of the other. Remember, that's how you find inverse functions. You solve for one variable. You solve for the other variable in terms of the original. Yeah, well, I shouldn't have. Okay, and then what's the area here? Okay, the area of the region is given by the integral from a to b, or c to d, that's more common, but the integral from a to b of, okay, in this picture, f of y minus g of y, dy. Now, I gave it away before. The idea here is we fix a y value strictly between a and b. We look at a representative line segment or a rectangle. A lot of books use rectangles, okay, where you have thickness delta y, right, that width delta y over here, right, that's dy, okay. Now, how do we determine the length of this line segment? We don't go top minus bottom like before. We go how? Right minus left. It's the greater coordinate. Remember, it's always the greater coordinate minus the lesser coordinate. The integrand must not be what? Must not be negative. So it's either top minus bottom or right minus left, okay? The integrand must be non-negative. Assuming that a is less than b, right? I'm assuming the standard setup. Okay, so bear in mind, if you do a u sub, then you can fudge things up, right? All right. Okay, so yeah. Here it goes, right minus left. Under the standard assumptions, right? Continuity and leading, right? Okay, you get that. Okay, questions? Maybe, for good measure, I'll write that out, right? If f and g are continuous, and f is leading g, maybe tying, on the interval. This is exactly analogous to what I had before. Okay. I won't mess with you on continuity. You got to worry about who's leading. Who's leading. In this case, who's on the right. All right. Let's do an example. All right. Questions? Again, the theory of calculus doesn't care. It's just that you care if you have to draw the region out. Okay, then it's kind of awkward to the eyes. Because you're not used to graphing bottom to top. You're used to graphing left to right. You're not used to graphing bottom to top. Again, I suggest you skim over 1.8. You don't have to be a master of this stuff, but you have to be familiar. Okay, but look at 1.8 in pre-calc. In fact, most pre-calc folks don't even have that kind of section. All right, let's do an example. This is 14 inch from House. Okay. Find the area of the region bounded by the graphs of, I'm going to write those extra words, bounded by the graphs of, these are easy, x equals y squared, and x minus y equals 2, is that right? Yeah, x minus y equals 2. What's that? What's the graph of that? It's a line. Yeah. All right. Now again, there's no set order, but let's talk about various issues here. Okay. For some people, it jogs your memory if you sketch it. All right. But first of all, well, I'm telling you right now that we can do a dy scan, which means solve both equations for x. Okay, solve both equations for x. Okay, that's for a dy scan. Now, right off the bat, you might be going, well, why am I trying for a dy scan first? Okay. Now, this is one reason why you might want to sketch first. Okay. But here's one reason. I'm looking at x equals y squared, right? And I'm thinking, you know what? If I can run with this, I would prefer x equals y squared to using a right plus minus a square root, right? Because if you solve for y, you get y equals plus minus root x. Okay. So here's the thing. This versus y equals plus minus root x. We're hoping that we can use this. Do you agree? Okay. I hope I can use this instead of this. Now, folks, sometimes you got to go with this guy. All right. So sometimes you got to go with that. But might end up having to do this though. All right. Okay, now if we can run with this, we go x equals y squared, add y, x equals y plus 2. Okay, so we have those two equations. Now again, step 2, you might want to do first. Okay, because you might want to look at the region first before you judge if it should be a dx or dy scan. Okay, I won't necessarily tell you on the test, use a dx scan or dy scan, so you should be able to figure it out. Okay, sketch the region. Okay, I often ask you to sketch it in reasonable detail. Not always. Okay, actually the problems that people have the hardest time with on the homework is when they can't graph it or can't graph it easily and they freak out, they don't know what to do. Remember, you can test values, folks. That helps a lot when you're studying the intervals. Sketch R. All right, this we should be able to do without testing necessarily. Although, I'm always going back and forth before we sketch. You might even want to do this first. Okay, you can debate which one to do first, solve, sketch, or whatever. What's going to be very important on our sketch? What's going to determine our limits of integration?
Intersection.
The intersection points. So, you know, you can debate which do you want to do first. It's up to you. You don't want to skip around. Okay, find intersection points. Again, we can skip around. Life is not always A to B to C to D. These are all mediocre. Okay, right here. Okay. So I'm going all the way to 3 now, so I'm going to go back and forth. That's okay, that can happen. I'm trying to emulate your thought process here, all right? Okay, solve. All right, now here, we can lean on this, right? Maybe we can do 1, then 3 maybe, but, okay. In fact, I'll refer to 1 here. Solve the following system. So I will refer to 1 here. X equals y squared, x equals y plus 2. Okay, you'll notice if you want to solve a system, sometimes you want to do step 1 too. All right? Okay. Well, a horse is a horse. Set these equal to each other. Y squared equals y plus 2. I have a non-trivial quadratic. What do I want to isolate on one side?
0.
0. 0. You're right, eventually y, but first let's isolate 0. Eventually y, that's true. Okay, y squared minus y minus 2 equals 0. Okay? Factor that. Oh, I ran out of room. Or QF. I should hope you know how to factor that, but if you're desperate, you can QF it. All right. Okay, y minus 2 and y plus 1 equals 0. All right. So y equals 2, or y equals what? Negative 1. All right. While we're at it, because I very often want the intersection points, so I want all coordinates. All right. Now, you can choose either one. These are both fairly straightforward. Let's do x equals y squared. That's okay. X equals y squared. Okay, so x equals 2 squared. That's 4. X equals, what's the square of negative 1? 1. So what's this intersection point? Is this intersection point 2, 4? No, it's what? It's 4, 2. Keep the order in mind. X is still first, then y. I know I'm going below the line now. Division line there. X first, then y. Okay? 4, 2, not 2, 4. This is what? First 1, then negative 1. Oh, I should circle these. These aren't my final answers yet. I should just circle these. All right. It still goes x, y. Okay, we have a couple of intersection points. 4, 2, 1, negative 1. I'm glad I have 2 and not none or 5. That'll be that's real trouble, real hard for me. Okay, so 2, I love 2. Okay, 4, 2, and 1, negative 1. All right. Although none might be okay, in which case you just test the value or something, right? Or look at the graphs. All right. Questions? All right. Wow, where are we? Okay, I'm going back and forth. That's okay, folks. Okay, you can kind of go back and forth between these steps. All right. sketch. Again, some of you may want to do this earlier. I'm kind of going back and forth. All right, folks, I said it. X equals y squared. X is a function of y. How do you graph x equals y squared? Parabola, opening, to the right. To the right. Okay? X equals y plus 2. Actually, x minus y equals 2 might have been easier for you. If you want to put it in slope-intercept form, you could say that this is y equals x minus 2. That's okay. Or intercepts. Just go by the intercepts. Okay? When we had x minus y equals 2 for that matter. Right? When we had x minus y equals 2. It might be easier to graph the original guy. How do you graph x minus y equals 2? Well, we know 2, 0 is an intercept. So is 0, negative 2. Okay, so 2, 0 is an intercept. And so is 0, negative 2. It's a line. Connect the dots. Let's see if the intersection points make sense. What was it? 4, 2? Makes sense, right? Makes sense. Here's 4, 2. All right. I'm going to need that 2, the 4 not so much. And what else? 1, negative 1 makes sense. In fact, I'll just cheat with the tick mark here. All right. I have to really cheat here. Okay. You can always adjust your graph. You can cheat, adjust your graph. Okay. When I say you can cheat, you know what I mean, right? Okay, kind of play with the graph a little bit. All right. Move your tick mark. All right. 1 negative. Makes sense, right? Right. 1 negative 1 makes sense. So here's the region. You agree, which is better, dx scan or dy scan? Dx scan goes like this. If you do a dx scan, look at my notes. You're going to change your bottom. That's trouble if you have to change your bottom, right? You have different, you need 2 intervals. dy, it's smooth. Same right, same left. Same right, same left. Same right, same left. Okay, consistent, 1 integral needed. All right. So it's easier. It's easier the dy way. You have to get used to it. Step 4, we're going to set up the integral. Area is integral from what to what? It's from negative 1 to 2. Okay, not 0 to 4. Negative 1 and 2. Of, we think right minus left. We're doing a dy scan. Okay, again, if we fix some arbitrary y between negative 1 and 2, strictly between negative 1 and 2, take this guy. All right, this point here, this point here. Okay, it's the x-coordinate on the right. Really, it's the x-coordinate on the right minus the x-coordinate on the left. Okay. Given this y, who's to the right? What is this? It's the line here, right? It's the line. The line says x equals what? Y plus 2. Y plus 2. Just to be safe, I put parentheses. Turns out I don't need them. Minus, and then who's this guy? X equals y squared. I trust you can do this. I trust you can do this. Y plus 2 minus y squared. Okay, they were the 2. dy. You could do it the dx way, but you know what? You're going to have to do this piece up to here, up to 1, and then this piece over here, with the line as the bottom, from 1 to 4. You're going to need 2 integrals, and it's a mess. You're going to need 2 integrals. It works, but you see my notes, have fun. If you want to see how to do it, look at my notes for how to do it the dx way. You can do it, have fun. You have 2 intervals. You can do it though, but you want to be efficient. Okay, the region is much better suited for dy scan. Hey, if it doesn't work out, try the other way. All right, we're at 8:25. All right, that's 6:1. You'll have the homework and everything. Next time we'll start 6:2, and I'll take questions. By the way, even if you don't have questions, come by. You're going to want to look at 6:2 because a lot of people think that, if you thought word problems are hard, a lot of people think that 6:2 and 6:3 and 6:4 are very tricky. Some people find those to be very tricky.
Do you have the answer to this?
Oh, the answer. Yeah, okay, that's the setup. Yeah, the answer's in the notes. What is it? It's